Happy to welcome Alberto from CERN. He will talk to us about the infrastructure project that he is leading for the last 4+ years, ETICS, now ETICS 2, which is the second iteration of this. And I'm looking forward to interesting insights into a true grid offering. Have fun. Thank you.
Thank you, Jürgen. Good morning, everybody. I hope you can hear me. I have a weird voice this morning, and I hope it will hold until the very end. So, first of all, I would like to say that it is a real pleasure to be here. The passion and enthusiasm I can feel around me are really great, and the quality of the people of the presentation so far have been really impressive. So far. So let's move to my own presentation. So in the next 45 minutes or so, I will talk about ETICS. ETICS is a project which has been established to become a sort of a software engineering infrastructure for research projects in Europe. It's a pan-European project sponsored by the European Commission. So first of all, I will give you some background about what the reasons behind ETICS, starting from CERN and LCG and EGEE projects. Then I will go more in detail into ETICS as a build and test system, and end with some of the challenges that we had to confront with next steps and conclusions. I put here a small glossary. I'm going to mention a number of acronyms in case you have doubts or get lost. You can refer to this one or ask me. So let's start with CERN and LCG and EGEE. So as Jürgen said, I come from CERN, and as you may know, CERN is the European Center for Nuclear Research, and is, you can say, is the biggest European and one of the world biggest research laboratories for nuclear physics, for particle physics. It was founded 55 years ago and has currently almost 21 members, mainly from Europe, but with many other participants, observers, or associates from all over the world. And it is also known as the place where the World Wide Web was invented. You may recognize Tim Berners-Lee from this picture. He was working at CERN when he invented the HTTP protocol. So one of the current major endeavors of CERN is the LHC, the Large Hadron Collider, which is a machine, is a tool, is a big ring running in the underground beneath the border between France and Switzerland, where physicists will try to accelerate hadrons, that is large, heavy particles like neutrons and protons, and smash them one against the other at very high speed and very high energies, to see what happens, to see what are the effects of this collision, what comes out of this, and to try to identify particles, different particles, and especially particles that are known by theoretical models but have never been observed in practice. Now, to validate a theoretical model, you need to have a practical, experimental observation of this. And one of the major expected results is the discovery of the mythic Higgs boson, which is the last missing pieces in the unified theory, which will actually sort of prove that the current theory are correct. If it is not found, it will be a lot of fun for physicists trying to find another unified theory. Now, this is a major endeavor and requires supporting major computing and data infrastructure to work with. So this is the LHC computing grid. It's a collaboration between various parties, so the physicists, the scientists doing science using these tools, the infrastructure and middleware projects developing the actual distributed computing and data infrastructure where all the data can be collected, analyzed, reconstructed, in the hope of finding new interesting evidence, and the actual service providers for the underlying network services and everything that is needed to keep this big, huge machine running. It is a worldwide collaboration. You can see the yellow dots are different sites participating to this effort. It's made of almost 150 different institutes all over the world in 35 countries with thousands of users and growing. In parallel to that, and a bit overlapping if you want, is another project called EGEE, which is enabling grids for EScience, which is a project started about 6 years ago by the European Commission to extend and enlarge this distributed data and computing infrastructure to other sciences, not just high energy physics, but any other science that may require this kind of computational and data management capabilities, from life sciences, biology, biomedical sciences and research, oceanography, astronomy, or humanities like archaeology or other sciences. It is a very large scale. It's probably the largest scale collaborative endeavor in Europe, and probably among the biggest in the world. So this is the background, and ETICS is born out of this experience. So in this kind of extremely distributed infrastructures, you have hundreds of institutes, thousands of people working together, not only for the actual physics, but to provide infrastructure, the middleware and applications used on this infrastructure. It becomes difficult to find a common way of working together, especially in software development. You have to take into account that it's very difficult in this environment to actually force anything. People come from different institutes with different cultural and technological background. They are used to use different operating systems, different languages, different ways of developing software. They have different skills, from very young graduates to very experienced senior architects. Now, since it is very difficult to force any particular architecture or any particular language, the decision was taken to try to find a way of hiding the complexity and provide collaborative tools where people can efficiently collaborate, bringing their own experience and their own skills, but with the common interfaces that everybody can efficiently use. In addition to the actual software development, here you have a pictorial representation of various complexity operating systems, different languages. There are different types of dependencies among different products. It's not just dependency in the sense of libraries, but functional dependencies, services needing each other in order to provide other services. And on top of that, you have emerging standards, at least in this particular grid world, for web services, for particular data management standards, computing standards that the different services have to try and comply with. And since these are emerging standards, of course, as in all emerging standards, there are 4 or 5 versions of each standard, which defeats a bit the purpose of being a standard, but it is a natural process, and it is necessary to converge and try to collaborate together. And on top of that, you need to do some testing. It is, of course, very difficult to believe that all the different pieces are developed in different institutes and put together and they magically work. So how to do this? The ETICS project was actually started to try and create this collaborative environment for software engineering, testing and quality assurance for these projects. At the moment, ETICS has about 45 different registered projects. Not all of them are particularly active. There are about 10 very active in using all the different features, but they cover about 60-65% of the total development in Europe. It stands for E-infrastructure for testing, integration, and configuration of software, which you can happily forget. It's called ETICS. And E-infrastructure is important. Apart from the E, when the E was mandatory when submitting proposal, because everybody had to be called E something for showing their commitment to the evolution. But let's say it's an infrastructure in the sense that it's not just a tool. It's really an infrastructure made of tools, processes, resources, machine, people, to provide this sort of collaborative environment for everybody to use. And its goal, its purpose is really to try to do very distributed testing, integration, and configuration of the different software, middleware, and applications produced for this computing and data grid. It was funded partially by the Commission, the European Commission, and partially by the participating institutes in 2006. And now it is ending its second phase, which will end in February 2010, next year. And after that, all the software, it is open source, will be released as open source, completely open source, with some mechanism to be decided and possibly, hopefully, used by taken by the community or integrated in other ongoing projects. It is a consortium among 8 different partners. CERN is the coordinator, and then you have the Italian Nuclear Physics Center, 2 commercial companies, experts in testing and quality assurance. You have other University of Wisconsin, research centers in Hungary and Germany, and Vega, a commercial company developing software for the European Space Agency. So all of them bring different perspectives and different expertise within the project. In a nutshell, very quickly, ETICS is essentially a continuous software build, test, and quality assurance verification system. It is designed to be as flexible, as extensible as possible, exactly to give people the possibility to contribute and to modify it to get the best out of it. Can be used for doing scheduled builds or tests or on-demand build and test by individual developers and users. And it can be used either locally on your own computer or remotely by using the grid itself. So the main objective behind this project is to use the grid resources to test the grid in order to be able to provide realistic environments where the grid can be tested. Because trying to test the grid, a real grid, the distributed grid, at least in the type of grid we are working with, in a controlled laboratory environment is completely mismatched. Because what happens outside is almost unknown in terms of interaction between the different services, the people, the network, and so on. So we try to provide realistic test beds, which are part themselves of the grid, as connectors to be able to push these build and test jobs down into the grid using various technologies, and we show some of these technologies. Has a repository where everything that is produced by the system is stored for public access, packages, test, build reports, test reports, compliance metrics, anything that is produced, and can be accessed using a standard package management system like YAM, which is a standard, for example, on some versions of Linux. And it is multi-platform and independent from specific language or build tools. It's not done for Java or for C++ or for Python or for Linux or for Windows. It tries to be as abstract as possible and to exploit the functionality of different operating systems in different ways. This is a pictorial view of the architecture. So it has a web portal where people can access to get access to the different functionality of the system, from configuration, repository, job submission, and so on. Clients written in Python to be as portable as possible for various, as many platforms as possible. A configuration web service and database where all the metadata is collected. So all information about the different projects, the packages, the test, everything is stored in a common place in order to be able to create relationships among the different pieces. The repository service, which stores the output of the processes, and the execution engines, which take requests from the user and distribute them to the grid for execution. And the actual place where the builds and tests are done are called worker nodes, which can be physical or virtual or a combination of them. And I will tell you more about this later. Authentication, authorization, and accounting is done using client and server certificates. This is very typical of the research grids. Almost everybody in the research grid has a certificate issued by some high-level certification authority, either national level or from very big institutes. For example, CERN has its own certification authority, but France or Germany or UK have their own certification authority. And they create certificates for the various research infrastructure. So you can access this system by using your certificate, and must come from one of these accredited certification authority. Now we are trying to change this because this is limiting, it's a bit limiting in terms of access. Many users are complaining that using certificates is too complex, and they would like to use standard username and password or shibboleth or Kerberos tokens, methods used in various domains, and try to integrate them in a single interface. you can access even without certificate or password, in which case you are guest and you can look at the data, but not modify it. And it provides quite a flexible authorization mechanism on the individual objects or different parts of the system. The current system is installed at CERN, and this is the address, ethics.cern.ch. When you log in with a certificate, you, of course, are identified as yourself, and depending who you are, you may see a different part of the system. You know, if you're an administrator, you see also the administrator tools, or you see different parts of the entire system. And from the web, you can see different parts of the information, so a list of projects, all the configurations, different packages. And for each configuration, you can see or edit, if you have the permissions, all the different properties, the build commands, the test commands, environment variables, properties. And this can be either global or per each specific platform you want to work with. And you define the entire build or test structure in this way. With the command line client, you can do essentially the same things as the web portal, but these are more designed to do build and test on your local computer or to integrate the system inside existing software engineering activities. If you already have a process ongoing, you can use the Python APIs to take part or all of the system depending on your needs. The repository, as I said, it contains everything that is produced by using the system in terms of build, test, quality assurance reports, and metrics, and dynamically generates these YAM repositories. So whenever you do a build or a test, everything is immediately available for chaining action. You build, you produce packages, and these packages can be used for deploying and doing configuration test or functional test. And it can be easily browsed or queried with various mechanisms. There is a REST interface that can be queried using XML or XPath syntax, and there are mirrors. There is a client, and there are mirrors on shared file systems like AFS for accessing them from other programs. This is how the repository web application will look like. You have a list of all packages and all the versions, and there are links between the packages and the jobs that have created those packages and vice versa, so you can see which packages have been created by a job or which job and which person has created a certain package. And for each package, you can extract all possible information and metadata to see what it contains or how it works. Execution engines, this is an important part of the system to distribute the various tasks for execution to the grid. At the moment, there are various ways of using this. So ETICS can work with existing submission engines. It uses existing batch system or grid submission engines. It started with Condor, which has been developed in the United States by the University of Wisconsin 10 years or more ago, which is one of the first grid systems for high throughput computing for parallelizing execution on multiple individual machines, not supercomputers. Then Unicore, which is actually the middleware, on the contrary, the middleware done for accessing supercomputers. Amazon Web Services, so we are experimenting a bit with clouds. This is really very experimental at the moment. gLite, which is the middleware used by EGEE. So this is really, gLite can test itself on the grid using it itself. And we are adding less grid-oriented, more batch system-oriented possibilities like LSF or PBS for non-grid users, for more conventional applications. So building with ETICS, just a quick overview, how does it work? So in principle, building with ETICS means using 3 commands. ETICS get project, this, and you specify the name of the project. This gets all the information about a specific project. For example, ETICS or gLite, these are projects. Once you have the information about a project, you can call ETICS checkout to extract the actual code or packages for that project. And with ETICS checkout, you can specify if you want to do full source build, everything from source, or a combination of source and binaries. For example, you want to build from source only a portion of the system, but you're happy to take from binary whatever comes from another project or all the dependencies. And this can be taken from any source. I mean, it can be version control systems like CVS or SVN, can be HTTP-enabled repositories, or can be any other repository of your choice by using plugins, pluggable pluggable connectors. Once you have extracted this, the system builds all the dependencies among all the different packages, and you can call ETICS build to build the whole lot. And you can build from a single package to an entire project of 2 million lines of code, exactly with the same 3 commands. And each individual package is built with its own commands. So this is the important part from the ethics and the infrastructure point of view. A project, as I said, is made of 10 different languages, so, 5 different compilation systems. And all of that has to be accessed with the same commands. So using ETICS build instructs ETICS to query, to use information for each package, and then activate the individual build commands and individual tools for each package, collect all the information, all the packages, and then create all the necessary links among all the products. And as part of the build, ETICS runs various types of test and validation, from static and dynamic test, runs unit test, coverage, standard compliance testing, creates packages, reports, and all that. So all the metrics are collected by using plugins. This is now is quite typical. I mean, you have to think this was started almost 8 years ago. Now it's much more conventional. So it is plugin based. Plugins are wrappers around existing tools, open source tools or commercial tools, or custom tools created by the users to add various types of functionality to the system. And they can be activated by user choice. So user may set profiles for each package, from high-level profile saying this package is Java, which means activate a whole set of plugins suitable for Java. Or you can specify individual tools that you want to run. Or you can ask the system to detect what is the best option using the auto profile option, in which case ETICS will try to understand what is the optimal set of plugins to run for your package and which metrics have to be collected. And everything is then pushed in the repository for later analysis, trend analysis, quality assurance verification, reporting, and so on. These are just examples. These are very common open source tools for various languages. At the moment, we try to cover as much as possible of Java, Python, and C, C++, which are the 3 most used languages. They cover about 70% of the total. A few screenshots. This is a typical example of this. This is an overview. This is the metrics overview page after a build. And for each metric, you have an overview page, again, for the specific metric. This is log count. And if a tool produces HTML reports, we just use them. Otherwise, the data is digested and formatted for the web. This is the output of CKGM, I believe, or check style. And this is the output of the IPv6 code compliance checker, which analyzes code to see if there are illegal commands, illegal functions from the point of view of IPv6 compatibility. Now, there is also a possibility of creating dashboards for users. This is user configurable, so users can give us an XML file containing which of the metrics they want to see displayed, or which information, like the list of builds or platform compliance and so on. And we can generate specific reports for each project. And another feature is the Atx Packager. So we try to isolate the developers from packaging, which is not always successful, and not everybody likes it, but it's very convenient. So in principle, we use the metadata information to create the packages, the most usable packages for each platform. So you can create your code and ask ETICS to build this code on 5 flavors of Linux, on Windows, on macOS, and Solaris. And ETICS will create the appropriate packages for these platforms. It covers about 80% of the packages functionality. And if this is not enough, you can overwrite it and do your own packaging, of course. The developers, in this case, the developers focus on the code and not on the packaging. And it allows to enforce strict packaging guidelines, which at the beginning was a big problem, because, for example, setting the right dependencies in the packages was a problem if you were working in Korea and using something developed in Paris. Like this, everything is centralized, and the information is much easier to identify and see what happens if you change something in the system. And finally, the metrics can be used to enforce something that we have created called the AQCM, the Automated Quality Certification Model, which is an implementation of various ISO standards, in particular ISO 9126 for quality assurance, which adds to the normal standards two aspects. One, practical implementation. The guidelines don't say anything about how you should do, but they tell you what you should do. We try to tell the users how they should do it, and puts a strong focus on the automation of the process. And use the metrics to measure the quality. I mean, I put measure within quotes because this is very subjective. It depends what each individual project considers as quality. And it has been recently presented in Rome to one of the ISO standardization working groups. And this was last Tuesday, and I've been told yesterday that it has been received with interest, which is much more than I was expecting. And it is an important starting point. Testing, let's go to the testing part. So you can test on ETICS in exactly the same way as you build with the 3 commands: get project, check out, test. The difference is that instead of getting things to build, the software to build, you get test to run. But the mechanism is the same, and you can also have dependencies between test and run different tests in different sequences. But this is for single node test. So you can run a test on a single computer, either your computer or the grid, but it's still a single computer, which is interesting but not so exciting. The important part is the multi-node testing. So this is a representation of, for example, of the gLite stack, which is made of many different services. And again, you see this is complete, but again, inside that picture, you can see already probably 6 different languages and different technologies in terms of web service, containers, security, and so on. So what we are trying to do is to find a way of actually deploying all that completely automatically. So if I want to test an application on a particular version of the grid, which is not used in production, something new, an individual user has absolutely no way of installing a grid first to test its application. So what we are trying to say is, please tell us, from your application point of view, which services you need to work with, up to the point of saying I need the grid as a bunch, as a whole lot. And then the system will deploy the grid for you and run your application and your test for you, and then clean up everything and give you the results. And you can mix and match different versions of the different services. But you don't have to know, as an application provider, how to do that. Now, there are several challenges in this, as you can expect. So first is a service synchronization. So you have a combined multi-node test made of 10 services, and they all have to be deployed on 10 different worker nodes. So the worker node, the different services have to synchronize among each other. So they start, and they maybe have to stop waiting for another service to do something, and then restart and publish some information, and et cetera, et cetera. And there is a need for exchanging information. Some task on one node may require input from another task on another node, and they don't know each other because, again, it's like it's being the grid. We ourselves have absolutely no idea where the individual tasks are going to be run, which machine, which hostname, which IP address, even which part of the world this is going to happen. So the nodes have to be able to communicate to each other across all the layers of securities and firewall and barriers that they may have in between. And then flow monitoring, where to go home, when to go home. When everybody has finished, everybody has to go home. And when to abort. If you have a test that runs, is supposed to run for 2 days, and it fails after 10 minutes, then you don't want to wait for 2 days until the timeout is reached for having the results. So there must be a way of communicating to all the waiting nodes that something has happened. So this is done. It's a very basic approach, very simple approach. At this point, we are not trying to invent anything particularly clever. But this is based on a simple set of APIs: get, ETICS get, set, info, exec, and list message. So get gets a key value pair from the internal information system, and set sets a key value pair on the system. These are all web service-based ports. And there are methods for setting, for logging, etc. EGEE is an instrumentation method. It allows to run commands on another node, but not arbitrary commands. So you can run the high-level commands that the service is exporting to you. So you can start, stop, load, unload, configure, and so on. So let me show you a very simple example. This is a hello world type of example. It's ping. So we have a client and a server, and the client has to ping the server. Very dumb, but it's to prove the concept. And the client has, of course, have no idea of where the server is, what is his name, IP address, or when it is going to be available even. They are submitted and they may land in completely different parts of the world. So these are the two parts. You have the first part is the server, which does an ETICS set of its own IP address. And on the other hand, you have the client, which as part of its commands does an ETICS get of the server of the same variable with a timeout. -b means timeout. It says, you know, I need this, and I will wait for a certain amount of time until it becomes available. This is how you submit it. You submit the entire multinode test with a single command. You don't submit each individual test. You submit the multinode test. And you can specify if you want, I hope it's readable. Yeah. You can specify if you want to submit the entire test on the same platform or multiple platforms. So you can submit the same multinode test on Red Hat 4, on Scientific Linux 5, on Windows, on Mac OS, on Sun, and all the different nodes will be of the same platform. Or you can mix and match. So you can say, I want to run the client on Mac OS and the server on Windows. And then internally, the system will allocate as many nodes as necessary and distribute the different tasks to the various nodes. So this is what happens during the execution. The client executes his ETICS get command and then waits until the server is able to give the result back or there is a timeout. The server, at the same time, somewhere else in the world, does an ETICS set for that IP address. And when this happens, the client is notified and then uses the information to continue. And then everybody goes home. Now, there is a huge problem with this, which is resource allocation, of course. So what happens, in the first implementation, the composition of the resources were fixed in the sense that all the different participating sites had a number of physical machines installed somewhere with the specific platforms. Now, let's assume you need SL5, which is SL5 is a clone of Red Hat 5, used for scientific applications, scientific Linux 5. You need SL5 64-bit, but all SL5 64-bit platforms are taken. So you have a multi-node jobs requiring 10, 15, 20 SL5. And after the first 10 have gone through, the other 10 have no place to go, and they have to wait. So at the end, the test may never be executed, because by the time a new platform becomes available, the first one may have reached its timeout, and the test is aborted. So issue one, the job are queued, and at the same time, many other computers are idle, not doing anything, simply because they don't have the right platform for this job. The second problem is what happens if there are obsolete or rarely used platforms. So nobody except one small project use Red Hat 7 anymore, but we need to support this project. This means that there is a platform, a computer with Red Hat 7 idle for 95% of the time, while every other platform is struggling for resources. So, of course, we want this to be dynamic. Now, consider this like poor man clouds from us. It is our first attempt at doing this, So in principle, we assume that all the machines are whatever they want to be. It doesn't matter which platform they run, as long as they can support virtualization. So they have to be some type of hypervisor installed. And at the moment, we support VMware, KVN, or Xen. And when a job is submitted, it contains its platform requirements, and the appropriate virtual machine is instantiated. So whatever is needed at a given time is instantiated, and all resources are always used to the maximum of their capacity. Now, this is not as simple as it may look, because we cannot just virtualize the worker nodes. So there are several problems with this. First of all, the worker nodes are attached to their submission node. And the job submission engines normally have a server and a client part. The client part has to be installed on the worker node. So in order to make a virtual machine look like a worker node, we would need to install the client part of the submission engine on each virtual machine for each platform. So this sort of makes the number of images that we have to support explode, because we have to have an image for each type of worker node, for each type of platform, and for each type of submission system. Now, and this is a huge maintenance issue, of course, because they have to be modified every time there is a change in the operating system or the worker node, the submission engine client. Even if we could do that in terms of maintenance, the second problem is that most of these submission engines are not very elastic, in the sense they are not dynamic. You cannot say, hey, I'm a new worker node, I've been just instantiated, please use me. There must be a link between the submission node and the worker node established with configuration on the server. So even if we instantiate a worker node, the server will never realize there is a worker node. And another issue is that not all the type of job submission engines support all platforms. So in any case, for certain job submission engines, we would have to limit the number of supported platforms. So we did it in a different way. As far as the job submission engine is concerned, there is no modification to the actual worker node. So the worker node client is still a physical worker node client. But then instead of shipping a normal ETICS job, the ETICS job comes with a program called the Bootstrapper that downloads the appropriate image. So this is now running in the worker node. The Bootstrapper downloads the image. It interacts with the hypervisor software to instantiate the image and boot it up, then transfers to the virtual image the actual task to be executed, and at the end brings back the result. So as far as the submission node is concerned, there has been no virtualization. It's still a worker node. But the actual task has been executed inside a worker node of a possibly completely different operating system. So challenges and conclusions. So challenges in all that since the beginning. I'm talking about a work that started about 7 years ago. So the first one is our techno-cultural challenges. So the academic research environment has a limited focus, or had at least. This is changing, luckily. Limited focus on software processes and quality assurance. It is really hope there are no scientists here, apart from computer scientists. But there is a completely different approach in how software is developed. Many scientists have a need for a tool that works now, and they are not really interested, for understandable reason, to maintain this tool or to make sure that someone else can maintain it or can use it in 2 years' time. So it's more based on discardable prototypes, not in the sense of agile, but really prototypes that become permanent, installed in some server and not touched anymore. And as the research infrastructure grows, this of course is not maintainable, because there are pieces of software that nobody knows how to maintain anymore, and the documentation is very limited, or the software has been written with very poor computer science skills. But this requires a profound change in the way software is developed for these activities, and change especially in the training of the developers and how the software development activities are performed, which is a change not really in the developers, but in the management, ourselves, myself, to make sure that they are properly trained and properly informed about what has to be done. Security is another challenge. So at least originally in science there were very little, not attention, but very little need for security. All the information is sort of public. There is no confidentiality issue, more or less. But this is changing as the scientific communities have been enlarged. If you start working on biomedical applications, then you have a confidentiality of the data. The patient information cannot be simply put on a web server. It has to be anonymized or pseudo-anonymized. It has to be transferred. There are international law regulations for privacy that have to be taken into account. So all this has to be considered now. And this changes also the way the software is designed. This must be taken into account at the design level, not just adding, moving from HTTP to HTTPS on a web server. It's not just superimposing security that this works. And the third challenge is sustainability. So how to move this? There is research infrastructure for something that is, at the moment, largely sponsored by the European Commission for creating it, but should become sooner or later a commodity for scientists. And sustainability also, not in terms of becoming a commodity, but becoming also self-supported. And this requires to introduce real business models in this kind of activities, so that if a service which has by then become standard can be provided, for example, by a commercial company or a system integrator, etc., rather than a university, it is a much more sustainable model, and the European Commission is encouraging us to go strongly in that direction. So there are two new initiatives starting next year called EGEE and EMI, the European Grid Initiative and the European Middleware Initiative, which have been tasked with this challenge. So the outcome of these two projects must be, please don't ask any more money to the European Commission. From now on, you are on your own. Now, this is a bit too strong a statement, but certainly the idea is we should find ways of moving this more into the community, or having ways of making this more commercial or business oriented, and hide the users from this. Our users are scientists, not computer scientists, are physicists, biologists, oceanographers, astronomers, and they simply want to have a tool. They want to have a web portal, an application. I need this. I estimate this may take so much time, and I need so much memory and this kind of bandwidth. This is probably even too much for a biologist. But all the intricacies of how this has to be done and what are the security models, etc., or how to get resources has to be completely hidden from them. And this is a huge challenge. So in conclusion, I believe, I'm proud, I can say what we have done in the conditions we have done it. I can say that ETICS has established a real distributed facility for software engineering in Europe, in this kind of research infrastructure, to analyze and hopefully improve the quality of the software that is being developed. And we had several challenges to confront, to address, and we have done it, we are doing it. There is still a lot of work to do. But we have hopefully raised the bar a bit in that, and we have raised the awareness in many communities, and hopefully also the level of the decision-making powers, the level of the European Commission, on the need of making these processes a bit more sophisticated and a bit more professional oriented. If you want more information, there is a website, www.eticsproject.eu, or feel free to contact me anytime. And with this, thank you very much.
Thanks a lot. This was very interesting. I'm sure there are quite a few questions out there.
Yeah, I have one question about the distribution. I guess, well, actually I have two. So I guess you anonymize the data so that it can be distributed to whatever data center is available for this, so that you don't have to worry about privacy issues, or did I understand it correctly?
Yeah, in some cases this is done, yes.
Okay. Then about the distribution, so I guess the individual participants in the project host these data centers. So how do you handle the cash flow between the participants, or is it just because they are participating in ETICS that you can use resources from whatever research institute is, happens to be available and has suitable nodes?
Yes, so there is a very particular concept in the research infrastructure, which is a VO, a virtual organization. So a VO is really an organization of people, resources, and sites. So in order to work with in a particular community and access particular resources, you have to be registered with a particular virtual organization using your certificate. And once you are registered, you are given access according to established rules to to a share of those resources. And all the anonymization of data, etc., is still based on these credentials. There are key stores. There are ways of the sites don't have access to this. Even if you store information on a particular site, the sites themselves cannot decode the information.
Thank you.
Hello, my name is Ji Yongzhang. I come from the VMware in Switzerland office. And just now you mentioned that in the ETICS project you're using VMware. That's very good. And thanks. And my question is that normally during the test procedure, some tests may take a very long time, say maybe 1 week or even longer. And somehow maybe at the end of, near the end of the test procedure, there's some service failed, and then probably we couldn't get the result we expected. So is there a way that, or any mechanism had been implemented in the ETICS project that can let the use the whole procedure to be recovered in the middle point or somehow, and then can save their time to rerun the test? Thanks.
Thanks for the question. Any other question? Yes and no. So, I mean, all the information, it doesn't matter when the test ends. If it ends successfully or it is aborted, it doesn't matter. Everything that has been produced until that point is recovered. Now, we are implementing now a way of actually storing the entire virtual machine, not just the data. So, I mean, the main problem is actually storage at this point. And storage for us, not in general, because storage is actually can be easily found, but we don't have enough storage in the project to do this. But we are experimenting with this concept. So upon request of the user, instead of bringing back the actual, a file, we bring back the entire set of virtual machines, images, snapshots until that point. So you can actually replay them, modify something, and replay and restart from the point where you left. But this is not even experimental. This is almost at the thought. I mean, it's the design level, let's say. But yes, it's an important point. Sorry?
So what I think is that it's based on each individual applications. It's not have a general global mechanism to automatically recover the reset test environment.
No, it is global. It is global for ethics, and so this is an ethics option. So you can say, for this test, please bring back all the images that have been used for this test, not for a particular application, but all of them. So if your multi-node test involved 15 nodes, you get 15 images, one for each node that was involved. You can reinstall them yourself on your hardware, or resubmit these 15 machines and restart from the point where it was left.
Okay, thank you. That's also one difficulty I encountered during my work. Thanks.
If I'm next, what's your schedule for open sourcing this?
It is open source. I mean, it is already is released under Apache 2 license.
Beautiful.
It can be taken. At the moment, is on our website. At the end of the project, the idea is to release it a bit better in a more common mainstream open source repository, SourceForge or something like this. But at the moment, for legal project requirement, we have it on the CERN servers. But it's still publicly accessible. It's a completely open source Apache 2 license.
Thank you.
If no one else comes, I had a question. Could you talk a bit about the size of the system? So how many users you have, how big's the code base, right? But what's going on every day on the system? How many nodes, worker nodes are there, etc.?
So there are several levels. So the system, the ETICS system itself, I don't know exactly the number, but we are talking about 600,000 lines of code in Java and Python. Users, there are almost 300 users registered at the moment, 45 projects, of which 38 are active in the sense that they have submitted either a build or a test in the last 30 days, and about 10 which are very active in the sense that they use it on a regular basis. At CERN, we have our own pool, which is about 150 cores, and then the grid. I mean, it is in principle that is only limited by the available cores on the grid, which is at the moment is 150,000. Is that possible? Something like this. But using this VO mechanism, so ETICS is a VO itself, and has a reserved share of these resources on participating sites, and this changes depending on the needs of the site. So, closer to a release, a particular site may decide to allocate, I don't know, 10% of its resources, and far from the releases, it's only 1% of the resources, so it keeps changing.
Hi, good morning. Can you maybe talk a little bit about the staffing of these efforts? How many people are involved? What's the management structure of the teams that are doing this?
Of ETICS itself. So ETICS, well, the activities around this kind of build test systems and quality verification started 6 years ago as part of the first EGEE project. So at the time, 6 years ago, ETICS did not exist, and we started when we started, we were 3 people. And we created the first version of the first version of the system, but at the time it was based on cruise control, not on our own software. And because at the time cruise control was the best tool we could find in this domain, but we had a number of problems. Namely, it was very Java oriented, and we had many other languages coming through. So we customized the cruise control, or we put a sort of layer on top of cruise control to use it. But at the end, when the first EG project finished and ETICS was created, we decided to design the system from scratch. And in the first ETICS project, there were 10 people. Then the last ETICS phase, which is finishing now, we're talking about 30 physical bodies, not all of them working full-time on this, on ETICS. But yeah, around, depending on the phase of the project, between 25 and 30 people across the 8 partners that I mentioned. So some at CERN, some in Italy, some in Hungary, in Germany, and so on. And if you want to know about the cost, the first ETICS project was sort of 1.1 million euros. And the second is about 2.8 million euros. So we're talking about 4 million euros in 4 years. Not all paid by the Commission. It's not only taxpayers' money, it's also the individual universities paying for this, which is still taxpayers' money. But
maybe I have one question if nobody else has one. On the testing side, how do you visualize the results, and do you know how much percentage of tests are actually running on this infrastructure, and who is paying attention to the results?
Yes, this is an interesting question. In the sense, so all the tools are there, all the tests can be visualized. In the sense that for the unit test, you have a complete list of all the unit tests that have been run and the coverage, etc. And for the functional test on the multi-node, you have the report, so you see exactly on each node what happens. So from a reporting point of view, we can see everything. The problem is, this is one of the challenges, very few of these projects actually have something to run on this. So at the moment, the average of coverage of unit test, for example, across all the projects we are working with, is about 26%, which is pretty low. In terms of functional test, there is one project fully using the functional test, but I cannot tell you, I don't know exactly how many tests they have or what they do with this test. And all the other projects are doing some experiment with this. Now we are working with gLite, which is the biggest, to start doing more functional tests with them for first deployment configuration test and then functional test using the multi-node. This is still very the beginning.
have one more. So if I heard this right, the objective of the current phase is to basically phase out of building this infrastructure, have the objective to establish it for good and for longevity, and then CERN and other research organizations can use that infrastructure ongoing.
Yes.
And the anticipation is there will be no group to maintain this and fix it and you know, all the nasty part of software development. Is that true?
No, well, it's a bit too extreme. So in the sense that it's not true that there will be no group to maintain it, but the hope is that there will not be any more CERN or a research institute to maintain it. So either becomes a fully community open source project maintained by the community, or, and this is what the commercial companies in ethics are trying to do, it becomes something maintained by the commercial companies, still open source, but they use it, they are doing marketing now themselves to use it for providing services, and therefore they will extend it and do maintenance for their own interests. Then, in addition to this, the model is actually to have the infrastructure maintained not by central funding from the European Commission, but to have the national research programs to contribute. Okay. So these are called the NGIs, the National Grid Initiatives. So every country contributes to the entire European infrastructure in various ways, with money or with resources to do some task. So, but the effort is really to get this out of the research infrastructure and move this more to companies or dedicated maintenance teams.
Okay, I think that concludes our first hour of the day. Thanks a lot.
Thank you very much.
Are you? Then let me hand this over.